Hello, everyone, and good afternoon. On behalf of Sampa Finland, I warmly welcome you all. This is the first seminar on a series called Sampa Open Talks. The idea in this series is to talk and discuss, learn, and also network, and talk about different topics on composites from experts in the field. And we are honored to have Professor Ignace Verpoest from KU Leuven as our first speaker, which will be on history of composites and life cycle assessment. So just a bit about the structure of the talk. There will be, after me, there will be a short biography of Professor Verpoest, and then we will have something around 25 to 30 minutes discussion about history of composites, presentation from Professor Verpoest. Then 5 minutes questions. So you can write your question in the chat, and then we will transfer to the professor. And then the next around 20 minutes about life cycle assessment. And again, we will have questions and such. Meantime, I will post in the chat our address of a YouTube channel where you can later on check the recordings of the session, follow our LinkedIn page of Sampa Finland for upcoming events, and for the website there's also address and email where you can give feedback and ask questions and suggest, for example, future events, what kind of topics, what kind of ideas we can have. So thank you once more, and I will then give the talk to Mikko Kanerva for introduction.
Okay. Yeah, thank you, Farsin. So my name is Mikko Kanerva. I'm one member of the Sampa Finland Club board, and also I'm an associate professor in Tampere University. It's very nice to see that we have people from different parts of the world. I'm actually currently myself in Kyoto, Japan. So we're having here meetings for planning a conference in the field of the aeronautics. So it's very clear nowadays that people work from different sides of the world, and we need different kind of communication tools, and people actually use many different kind of channels nowadays to follow each other, gain information, and follow either online live or then recordings afterwards. That's why board of Sampa Finland, they came with this idea of the talks, and I think it's great. And I thank also the Sampa Europe for the support for this kind of concept. Okay, but we are starting this row of talks with a very great talk, which will be given by Professor Ignace Verpoest. So I want to have the honor to introduce him, and I will give a bit introduction. So Professor Ignace Verpoest got a master degrees 72 and PhD 82 in materials engineering at the Catholic University Leuven in Belgium. As a full professor, from 1990 to 2013, he was guiding group which consisted of 8 postdocs and researchers and 25 PhD students in average. So a big group. He's author actually of more than 370 journal papers, about 500 conference papers, 4 books, and holds 15 patents. Professor Verpoest was a visiting professor at several universities, such as Stanford University, École Polytechnique Fédérale de Lausanne, Kansai University, Université Catholique de Louvain. Since 2013, Verpoest is emeritus professor at KU Leuven. He continues to be involved in research projects on carbon fiber and natural fiber reinforced composites. He has special interest in the history of composites. Hopefully, we will today hear more about this one. Just to add for this bio, I can also tell that Professor Verpoest is the holder of Doré Chair in Composite Materials at KU Leuven and chairman of the European Scientific Committee, the European Confederation of Flax and Hemp. He was also president of the European Society for Composite Materials and of the International Committee on the Composite Materials. He was chairman of the Materials Research Center at KU Leuven and is a member of the Royal Flemish Academy of Belgium for Science and Art. During many years, Professor Verpoest won several awards, among others, the Descartes Prize for Science Communication of the European Commission, the International Fellowship of the Society for the Advancement of Materials Processing and Engineering, so SAMPI, and of the International Committee on Composite Materials, ICCM. He was also awarded the Medal of Excellence in Composite Materials of the University of Delaware. In addition to the academic career that he has, he's also co-founder and board member of the company Inaugural, worldwide producer of innovative honeycomb cores, and co-guided the startup of the company Verpoest, which produces hybrid carbon steel fiber reinforced composite bicycle frames using a very special process. I believe today we will have a great talk, and I feel that it's my time to give the podium to Professor Verpoest.
Thank you very much, Mikko, for this very nice introduction. Yeah, after being for almost 40 years in the composites field, one accumulates not only publications but also awards, and when you all see them in one presentation, it's a little bit too much, I think. Anyway, I'm very happy to be invited to give this double talk, one on the history of not so much composites, but carbon fibers, because the history of composites would require a whole afternoon, I think. So I will focus on the history of carbon fibers, and then the important topic of life cycle analysis of carbon fibers in the second part. I will share my slides, and I hope that will work. So, do you see the full screen now?
Yes, we can. Everything is okay.
Okay. So, the title of the first part of my lectures is The Invention of Carbon Fibers, an Exciting History Asking for Further Exploration. On the website of JEC World, and you see the URL there at the bottom of the slides, you can see a kind of timeline for the development or the history of composites, and that was made up when I wrote this booklet on the history of composites. 2 volumes have now been published by JEC World, and you can find an online version of those 2 booklets on the same website as you see it below. So I will be very brief about just glancing over the history of composites until the moment that carbon fibers were invented. So we already see long before our time, long before, let's say, the time of Egyptian and Romans, we see that the composite concept was existing, reinforcing bricks with straw, impregnating papyrus fibers with a kind of asphalt. But surprisingly enough, you can find already in the 18th century the first indications that Réaumur, whom we know from one of the temperature measurement standards, he also invented glass fibers. And the first machine to manufacture glass fibers was invented by a German living in the UK, Louis Schwalbe. The first moment that we read something about carbon filaments for electric lamps is linked to Edison, but I will come back to that at the end of the 19th century. And I will show that, in fact, already before Edison, some people had the idea of making carbon filaments. Then in the 20th century, we have the invention of the first man-made resin, phenolic resin, by a Belgian guy, Leo Bakeland, who at that moment worked in the US. Two of his collaborators then filed a patent 6 years later, which is, as far as I could reconstruct, the first patent which defines the concept of a composite material, namely a polymer, in their case phenolic resin, reinforced with textiles, and they were in first instance using linen textiles. And even more surprising is that already more than 100 years ago, in 1916, there was a very interesting patent which describes the construction of an airplane fully constructed out of composite materials as they had been described by O'Connor and Faber in their patent. More details you can find in the booklet I wrote for JEC on the JEC website. Then in the 1930s, we have three important inventions. Polyester was invented in early 1930s, epoxy resins a couple of years later, and then the first production of continuous glass fibers, which we could use for a reinforcement of composites, was done by Slater Games in the US, collaborator of Owens Corning in 1938. And in the same moment, then in the UK, Norman de Bruyne was making the first composites using phenolic resins, but with natural fibers. And then came the Second World War and the period after that, where we then see a strong development of glass fiber reinforced plastics for airplane components. The concepts, manufacturing concepts of filament winding and pultrusion were already invented at that time. The first sports applications were coming up with surfboards, the first automotive applications, and the first aerospace applications, full aerospace applications, gliders, were also in the 1950s. And then we come to what I call the second materials breakthrough after the first one in the 1930s, which is related to carbon fibers. And I will come back to this scheme in a minute. So just to remind you, we have the way we are making composites, or we are making carbon fibers as at this moment, well, 95% or 98% even, I think, of all the carbon fibers produced worldwide are produced starting from polyacrylonitrile. So first we do the polymerization of acrylonitrile, we spin the fibers, we stretch them a first time, we dry them, and then we stretch them a second time. The stretching is needed to realize a kind of molecular orientation in these PAN fibers. And then these PAN fibers are introduced in the oxidation and carbonization process. And if we want to have even more perfect carbon content up to 99.9% sometimes, then we have a graphitization process as well. And finally, a surface treatment to protect the fibers, but also to improve the adhesion with the matrix later on in a composite. Now, the question is, who invented the first carbon fibers? And I already referred to Edison, but in fact, already almost 50 years before Edison, there was a UK guy, Frederic de Molins. He was from French origin, and he had the first patent where he used powdered charcoal, which he heated between two platinum wires, and the charcoal started glowing and made light. Joseph Swan then added to it two things. First of all, he was using a filament of carbonized paper, and second, he was doing that in evacuated glass bulb, creating a kind of a vacuum which would improve the durability of his invention. And then comes Edison, and what Edison in fact has done is bringing this to a kind of industrial level. So he was not doing the initial invention, but he brought it to an industrial level by carbonizing natural fibers, amongst others bamboo. The problem was that these were still rather fragile, and it's interesting to see that Lewis Latimer, he was the son of an African slave, was working as a technician for other inventors, amongst others in the group of Thomas Edison. And he, in fact, made a very big step forward in developing a more reliable carbon filament, because all these carbon filaments were very brittle, and he encapsulated it in the cardboard. Again, I refer to my booklet on the JEC website for more details on this. Unfortunately, by the end of the 19th century, this invention became obsolete because tungsten wires were then used in glass bulbs for making light. And then we go 70 years further. And in between those 70 years, and there was a lot of research on carbon fibers, but not towards carbon. Was a lot of research on carbon, but not so much about carbon fibers. And the first signs we see towards carbon fibers were happening in the 1950s, where again natural fibers, amongst other cotton fibers, but also rayon fibers, were used as filaments to replace tungsten now. So they wanted to go back to the original idea of using carbon fibers, but this time in vacuum tube power amplifiers. 1957, there was a development by Barnaby and Cheney for making carbonizing natural fiber or rayon fiber mats and tows for thermal insulation and filter applications. And in union carbide, and you will see again later on, union carbide has been playing a quite important role. They carbonized rayon cloth, rayon textiles for rocket nozzle exit cones and re-entry shields. So all these things were not really aiming at mechanical or structural applications, except maybe the last one, but that was again mainly for thermal reasons that these carbonous materials were used. And the first person who really looked for fiber-like materials was Roger Bacon, again in the Union Carbide Company Research Center, Parma Technical Center of Union Carbide. And he, in fact, produced by first sublimating carbon and then condensating it. Sublimation was realized by a high voltage arc between carbon rods. And then the sublimated carbon was condensated and formed a kind of fiber-like, on a nano level, fiber-like material. And without going in detail, it's very exciting to read how they made a guess, in fact, of the Young's modulus, but he was reaching a Young's modulus of 700 gigapascal and an estimated tensile strength of 20,000 megapascal. And at that moment, my understanding is that all of a sudden, the carbon community started understanding that maybe mechanical properties of these carbon fibers could become an interesting issue. You see here the patent of Roger Bacon. And some people claim that, in fact, these nanofibers of Roger Bacon, which were very short, can be considered as the first whiskers, carbon whiskers, and hence, so these are carbon whiskers, but they can be considered as the first carbon nanotubes, which in fact only in the 1990s were officially discovered in Japan. So a similar attempt to make carbon fibers, but now not carbon nano fibers of bacon, but real fibers which you can handle, was done by William Abbott in the Carbon Wool Corporation, and he was carbonizing rayon fibers, but at very low temperatures, below 260 degrees, and as a consequence, the mechanical properties. No, they were really focusing on mechanical properties. The mechanical properties were very low and the carbon yield was only 50%, whereas now we reach much higher values. So this is the development at Carbon Wool Corporation. And then we go back to Union Carbide, and in the same group as Bacon, Ford and Mitchell then improved that approach, the previous one of Abbott, where he only was heating up the rayon fibers to 260 degrees. They were doing it up to 3000 degrees. And they were reaching monofilament strength of up to 900 megapascal. The interesting thing, however, in this research is that as far as I could reconstruct, for the first time, there was made a link between the orientation of the graphitic layers in the carbon fibers on one hand and the mechanical properties on the other hand. You see it here in the text below that they measured that by X-ray diffraction, and they say that a high degree of preferred orientation exists throughout the entire filament. And it is believed that this high degree of uniformly oriented crystallinity in part accounts for the superior strength of the monofilament. So this is, as far as I could reconstruct, the first time that this link was made between the structure of the graphitic layers on one hand and the high mechanical properties on the other hand. Anyway, the American Chemical Society claims that the real inventor of carbon fibers should be considered as Roger Bacon with his carbon whiskers on one hand, and then later on, but I will not dwell on that, Leonard Singer, who then started the commercialization, but I will come back to that. So we have carbon fibers. It was shown in America that they have interesting properties, but there was not at all any commercial production, and all these fibers were discontinuous fibers and so on. And then comes Akio Shindo in Japan. He joined Government Industrial Research Institute in Osaka in 1952 for studying carbon and, in fact, degradation of carbonous materials for nuclear reactors. And he said, I will not read it fully, but he said, in fact, that what he was interested in was development of industrial materials and not so much just the degradation of carbon fibers. Now, that story is for people who are interested in how science and technology develop, is in fact a very interesting case. Because it's very well documented now by a lot of research in Japan that in May, 29th of May 1959, there was an article in a Japanese business and technology newspaper, Nikkan Kogyo, which referred to a method to thermochemically make fibers, transforms fibers such as rayon into graphite, kokuon, as it's said in Japanese, by heating them to 3000 degrees. And here you see an image of that famous newspaper article of 1959. So because it refers explicitly to 3000 degrees C heating, my guess is, but there is no solid proof of that, is that that article referred to carbonizing rayon fibers the way Ford and Mitchell had been doing it at Union Carbide. This inspired Akio Shindo to refocus his research from degradation of carbon for nuclear applications to looking at using polymeric precursors, maybe not rayon, but others, to make carbon fibers the way it was reported it had been done in the United States. And only 3 months later, and that's really amazing, only 3 months later, he already filed his patent. So for people who have been filing patents, and I have a few of them, this is an unbelievable short time that from the idea, from the concept of the start of the idea of I could do that until the filing of the patent, it took him only 3 months. And I find this a textbook example of careful observation during experimental work that can lead to important scientific breakthroughs. And I will take a few minutes to take you through this invention of Shindo. So he said, okay, I need good fibers, and I will try different types of polymeric fibers to make carbon fibers out of them. And he finally ended up with DuPont's polyacrylonitrile fibers, the Orlon fibers. And he took one of these fibers, one single fiber, and put it in a tube, flushed it with nitrogen to get rid of the oxygen as much as possible, heated up to 1000 degrees, and he had immediately, or after a few trials, he had a non-brittle carbon fiber. And he writes in his report, it did not fracture when you wind it around your finger. And then he said, okay, one single fiber, that's not enough. Let's take a bundle of fibers who was doing exactly the same. And the fiber, the bundle of fibers, resulted in a brittle behavior. So then he started asking, why would that be? And in his thinking, it could be related to the amount of oxygen remaining in the tube which he flushed with nitrogen. That amount of oxygen might have been sufficient to create a partial oxidation of the single PON fiber, and hence to stabilize it, because oxidation of polyacrylonitrile fibers results in a thermal stabilization, so the fiber becomes heat resistant so that it can withstand higher temperatures for the carbonization, whereas there was not enough oxidation, not enough oxygen available for oxidizing all the PON fibers in a bundle of fibers. And hence he discovered that the oxidation process is the critical step in the production of carbon fibers. And by this very careful observation, what happens during a simple experiment, in fact, he laid the basis for one of the most important material revolutions of the 20th century. Now, the question is, how good was Shindo's carbon fiber? Well, there are different sources and they are contradicting each other somewhat. Some people talk about the fiber modulus of 110 gigapascal. McGill, in his book, mentioned 165 gigapascal and a strength which, depending on the type of polymer used, was between 700 and almost 1000 megapascal. And then Johnson refers in a book by Watts that he could increase, Shindo could increase the modulus of the fiber, the carbon fiber, from 110 to 160 gigapascal by increasing the carbonization temperature from 1000 to 2000 degrees C. I think we need, and I have in the meantime had some progress in that. We need some translation of the original Japanese patent, and I now have it and will study it further. Okay, how did it then go further? Well, we can say that the patent of Shindo in 7 September 1959 was in fact the patent which created the way how to make carbon fibers based on polyacrylonitrile fibers. He presented his results in a domestic conference in 59 and published his famous report in 1961, where he describes quite in detail the whole process. He also published several papers in Japanese journals, and he presented, he defended his PhD, which was translated in English, and then he presented these results another 2 years later in 1963, and you will understand in a minute why 1963 is important. In 1963, he presented his invention during a conference of the American Carbon Society in the US. So he also waited, but that's a small remark, until 1963 to file an international patent, but the priority date was already passed, so that was not accepted. Anyway, we have now a way of making carbon fibers from punk precursors, and the question is, what did the other people in the US and in the UK do to invent or to further improve that invention? Well, in the UK, it's very interesting that during a discussion in the Royal Society in London, William Watt mentioned to Tony Kelly, and Tony Kelly is, he died a couple of years ago, is one of the, Sir Anthony Kelly, one of the big names in composites, and Watt mentioned that he could make stiff graphite fibers. You can read this statement in a paper by Tony Kelly. And they indeed started doing it, and they could reach stiff carbon fibers with the stiffness up to 375 gigapascal by applying, and that's important, by applying tension during the oxidative stabilization process of the PAN precursor. They filed the patent in 1965, and here you see Phillips, Watt, and Johnson, the three co-inventors in the United Kingdom. In the US, we have Roger Bacon, who then, after his work on the carbon whiskers, collaborated with his people in Union Carbide, and they already started, also 1 year after the UK people started studying the effect of straining the fibers during the processing, during the carbonization process. But they were still hooked at rayon-based carbon fibers. And this straining, in fact, was also done by, and I will come back to that, by Kotlinski, another American researcher, who proved that by straining pyrolytically deposited graphite, they could also increase the mechanical properties. Now, why is this so important? And this is the one before last part of my presentation. Why is this so important? So we now know very well that the orientation of graphitic molecular units and hence the higher mechanical properties, so that the orientation is very important for achieving high mechanical properties. And this can be done, and we all understand this now, by applying tension or straining or restraining during the oxidative stabilization process. And the question is, who came after the initial invention of making carbon fibers from polyacrylonitrile, who made as first this second step? Because the second step of understanding the relation between the straining during stabilization, the orientation of graphitic molecular units, and the high molecular properties, mechanical properties, that connection is now considered to be a crucial second step in the invention of carbon fibers. The question is, who was the first who came up with this ID link between graphitic orientation mechanical properties and the oxidative stabilization process. Was it Shindo, who in Japan already in his first invention, in fact, unknowingly, in a way, was applying strain during the oxidative treatment of polyacrylonitrile fibers? I come back to that. Or was it in the UK, Watt, Johnson and Phillips, who deliberately looked at the effect of straining of PAN fibers? Or was it Kotlensky and later on Bacon who studied also the effect of straining on the mechanical properties? So looking very quickly through it, in fact, if you read attentively what Shindo has been doing, he fixes the PAN fibers on a frame to make sure that the fibers should stay straight during that oxidation and carbonization treatment. But he mentioned in one of his papers that not only the air oxidation is important, but also the orientation of graphitic molecular units. So he was aware that during his process, where he restricted the length of the PAN fibers, and as they are oxidized and certainly graphitized or carbonized, the volume of the material decreases, hence there will be created a tensile force during that process. Well, he understood already that this could create an orientation of the graphitic molecular units. So that's one school that says, yes, Shindo has also had that idea. The other school is, no, it's Watt, Johnson and Phillips in the Royal Aircraft Establishment. They were basically doing initially exactly the same as Shindo, winding fibers on a frame. But then they, and Kelly says that what they then did further, actively straining the PAN fibers during the oxidation, that was not done by the Japanese, which, as I explained a minute ago, is maybe an incorrect statement. Anyway, in the documents related to their patent, they state explicitly the effect of restraining of PAN fibers from shrinking during oxidation on both stiffness and strength is convincingly shown as a function of the carbonization and graphitization temperature. So they were aware that this is important. And by doing that in a more systematic way, and you can read those papers, they reached a stiffness of 400 gigapascal. And then there is Bacon and Kotlensky. As I said, Kotlensky already in 1962 did some initial research, but they were straining at the carbonization and graphitization temperature. And in fact, it was Bacon and his collaborator Smith who in 1964, which is almost exactly the time when Watson, Phillips and Watt, Johnson and Phillips in the UK were doing their experiments on straining, they also started stretching at the temperature of 2,800 degrees. That was not very effective. And then 5 years later, they published and filed patents where they said, you have to stretch during the heating, meaning during the oxidation phase, and then you can increase the stiffness up to 450 gigapascal. So for being effective, the stretching and rayon-based carbon fibers must happen and they still were working on rayon-based fibers, so they needed somewhat higher temperatures to do that than for PAN fibers, but that's a detail. So the conclusion is that Shindo was aware of the importance of some stretching during the oxidation and stabilization, but the first who really studied that systematically were Watt, Johnson and Phillips. And the question is, were they aware of what Shindo has been presenting? And I'm looking, I'm searching whether either Watt or Johnson or Phillips were present during the presentation of Shindo in the American Carbon Conference in 1963, because then it would be logic that immediately after that they started their own research. And were they aware, so the UK people, of the developments by Kontlinski and Bacon? So more research is needed to find out who was in fact how all this developed, this awareness of the importance of stretching during the oxidation and stabilization phase. So one, you have to say who has been inventing carbon fibers. My idea would be it's Akio Shindo. He has really started it in the earliest way. But on the other hand, also Roger Bacon has played an important role, and William Watt, together with Johnson and Phillips in the UK, have been also playing a role. So the University of Delaware, when they awarded their Medal of Excellence in 1987, made what we call a Belgian compromise and gave the Medal of Excellence to all three of them. So finally, I will still spend a few minutes in explaining what then happened after these two important things. The invention by Shindo on one hand, and then the invention on several places more or less simultaneously on the importance of stretching during the oxidation phase. So in Japan, in fact, Shindo was signing research contracts with Nippon Carbon, and they brought on the market the carbon fibers already in 1961. So Japanese companies were the very first to bring carbon fibers on the market. Tokai Denkyoku had a similar agreement with Shindo. They commercialized the Thermalon fiber. And both fibers were not so much intended for high mechanical properties, but for high temperature applications where these fibrous structures were more, the flexibility of it were more advantageous when in comparing with solid carbon blocks or solid carbon panels. But both companies, Nippon Carbon and Tokai Denkyoku, have a problem in the sense that they lacked experience in polymer precursor fibers, and they did not produce the PAN fibers themselves. Then Shindo licensed his patent to those two companies, but the major breakthrough was coming a couple of years later. So you have to realize that in the meantime, some production was going on in Japan, but Toray was standing a little bit aside until the moment that when they started the production of nylon 6,6 using aniline in an innovative process, then they patented a new polyacrylonitrile compound, which they called HEN. And they found more or less by coincidence that they could reduce the oxidation time, which was the time limiting factor up to then in the production of carbon fibers. They could reduce the oxidation time by a factor of 10. And at that moment, Toray decided that can be interesting. They started carbon fiber development in 1968, so that's 6-7 years after Nippon Carbon and Tokai Denkyoku. 1969, they start industrialization research, and they started the production of their first batch type carbon fibers, 11 grams for a 1 meter bundle in January 1970. And at that moment, they saw, okay, we can do that. And they obtained the practicable rights on the Shindo patent and all the rights on the developments which were done earlier by Nippon Carbon and Tokai Carbon. And they start there in 1971 their continuous process pilot line, where they start the first T300. And in 1972, in Ehime, where still is the main plant of Toray in Matsuyama, they have a production of 5 tons per month. In the US, they were still initially working on rayon-based fibers, that was not so successful, both in terms of properties and of carbon yield, of efficiency of the process. So finally, they turned towards PAN-based fibers, and they first got a license from a patent by Toho Rayon, and then Toray transferred their PAN carbon fiber technology to Union Carbide, the company where Bacon was working initially. And in Europe, also Toray and Toho Rayon started production, Soficar in France and Enka in Germany. And then in the UK, it's a very specific story. The patent from Johnson, Watt and Phillips was licensed to 3 companies. Morganite, they produced initially discontinuous fibers. It's too expensive. And Courtauld, which is a textile company, were the first to continuously process PAN fibers, and then they sold these PAN fibers and this to Rolls-Royce, and they filed several patents. It's a very interesting story. They filed their patents not in the UK, but in all kinds of other countries, like in Belgium, to keep it secret. But finally, they came up with the very good carbon fibers. They tried to make a carbon fiber fan blade for one of their engines, and that completely failed. And that's almost a bankruptcy of Rolls-Royce, but also the end of the carbon fiber manufacturing, more or less a couple of years later in the UK. So, as a conclusion, when you see, and this is a scheme I got from a very good paper translated in English, a Japanese paper, when you see, okay, we have in Japan from the very beginning a focus on carbon fibers based on polyacrylonitrile, based on the initial patent of Shindo. There were some initial developments by Nippon Carbon, but only it took off when Toray came into the scene and started producing their continuous carbon fibers in an industrial way. They licensed this technology then to Union Carbide and some others. In the US, they were limited to rayon fibers, and that stopped in the early 1970s. And in the UK, there was also developments based on polyacrylonitrile, based on the Royal Aircraft Establishment developments, but due to the, let's say, bad luck of Rolls-Royce, these developments stopped as well. So the invention of carbon fibers is an exciting but complicated story. A lot still is unknown. The interactions, as I mentioned already, between Shindo, Bacon, and Watt in the crucial period 1955, 1965. Details on Shindo's revolutionary work, discovery of the importance of tensioning and straining, who did what. So hence more research is needed, and I'm still dreaming of kind of creating an international working group on the history of composites, and more specifically, the history of carbon fibers. So thank you very much. In the paper in the booklet of Jacques, you can find a lot of references, and these are the most important references on carbon fibers. So thank you very much.
Thanks a lot, Ignace.
Yeah.
If you are ready, I can ask a few questions from Professor Robert Joffe from Sweden. So the first question is, I have heard and never seen about commercial isotropic carbon fibers. I am curious, what is main application of such fibers? I guess non-structural. So if you want, you can answer this if it was clear for you.
What is meant exactly by commercial isotropic carbon fibers? I think they have not, well, they have been developed and they were in a certain way isotropic when you take just rayon and carbonize the rayon, then you will only reconstruct the polymer orientation, which is anyway present in the rayon fibers, you will find it back in a kind of orientation of the carbon fibers. But because you don't have this stretching during the oxidation, you will not have a very well oriented graphitic structure. And whether that is then isotropic or not, I do not know. But it will certainly be much less anisotropic, much less oriented than what we have now after the straining, the stretching of the PAN fibers during the oxidation step.
And so I made Robert the co-host. If he wish, he can, of course, ask himself. But anyhow, the second question is, what about lignin-based carbon fibers? What is your view on future of those materials? Will they be as good as PAN-based fibers?
Yeah. I must admit I have been only reading by bits and pieces reports on lignin fibers. So I will give a kind of rather superficial impression. What I see, in fact, is that these attempts are not new to make carbon fibers out of lignin. Lignin has a very high carbon content, so it's evident that you could make carbon fibers out of it. But lignin has also a very, very complex molecular structure, much more complex than polyacrylonitrile, which is a more or less a linear polymer, and you can orient it very well during the production of polyacrylonitrile filaments. And then you reconstruct that into a very well-oriented graphitic structure. I'm afraid that is one of the main problems for the lignin fibers. And the fact that already more than 10 years people have been trying to make good lignin fibers might be related to that fundamental problem. Other people are mentioning the problem of the purity of the lignin material. If it's not perfectly pure, then you will have defects in the carbon fiber, which will lead to a lower strength of the carbon fiber compared to when you use polyacrylonitrile, which can be made extremely clean, extremely pure. And that is one of the strengths of companies like Toray and others who have the polyacrylonitrile production in-house. So they know that these polyacrylonitrile for carbon fibers has to be much cleaner and much more defect-free than the PAN fibers which are used for clothing for normal textiles. So that might be a second reason. So yes, it's interesting to have lignin as a precursor, but the fact that after 10 years we still do not reach the same properties makes me doubt a little bit whether we ever will be able to do that. And hence the door is open for other innovations. So why not try to make polyacrylonitrile precursor fibers based on bio-based chemicals, so that we have then also that process more or less environmental impact, that it has a lower environmental impact. Although not all the problems, I will come back to that in my second lecture, not all the problems will be solved then, because the process of polymerizing acrylonitrile and spinning the fibers is in itself, irrespective of whether it's a bio-based chemical or not, that process in itself is rather energy intensive and CO2 intensive.
Thanks a lot. So I think Robert is also quite satisfied with the answer. If you have time, I can ask maybe one more question, and then we can continue with the lecture. So you mentioned that, for example, Toray pays a lot of attention to produce in-house PAN, so they are much cleaner, defect-free. But I think in your presentation, was it Shinado reports, for example, when you use copolymer PAN, I think the properties was better. Doesn't it actually create some kind of issues when you have them?
Yeah, here we are coming into the, let's say, details of the chemistry of these polyacrylonitrile fibers. And I'm not enough a chemist to judge that completely. So the polyacrylonitrile is not, of course, just only purely polyacrylonitrile. And you see this hen component, which Torre has been adding to the polyacrylonitrile to decrease the oxidation time, which was before many hours, and then it was reduced to many minutes, a few tens of minutes. So that proves that the chemistry is not just polyacrylonitrile, but there are a lot of pepper and salt added to it to control certain properties. I must admit, I'm not enough a chemist, a polymer chemist, to give a lot of comments on that.
Thanks. I think it's already quite clear. And one more quick question. So I think again it was Finado who first carbonized one single fiber. It was more ductile, and then there was a like roving. It was more brittle because there was more oxygen trapped. So in the industrial
no, it was the other way around. So when you have too many too many PAN fibers, so he did do the same cleaning of the chamber with nitrogen to get rid of the oxygen. So he was doing the same for one single fiber and for a bundle of fibers. And if you do it in the same way, you have the same amount of oxygen, but that is just enough for oxidizing one PAN fiber, but was not enough. That was his hypothesis for a few hundreds of fibers. So that was the reasoning he made.
All right, thanks a lot. I think there is any other question, and you can, if you wish, continue with the other part of the lecture, which will be on life cycle assessment.
Yeah. So no further questions?
Not at this stage, at least. I have other questions.
Okay. Do just give me 1 minute of break. I get
Sure.
glass of water to save my voice. Sure. Just 1 minute. Huh?
Of course. So meanwhile, I shared the email address of Sampe Finland. So if you have any feedbacks on the lecture or ideas about the future event, please send us an email. Thank you.
Okay, I'm back. Will I start the next part?
Yes, please.
Okay. So let me see. Okay, so this is the next part of my presentation on LCA of carbon fibers, and I have given it a subtitle, Exploring the Reasons Behind the Hugely Diverging Published Data. I made this presentation and I worked on this topic for the last 2 years, part-time, of course, being retired, together with Professor Véronique Michaud from the École Polytechnique Fédérale de Lausanne in Switzerland, and Professor Jun Takahashi from the University of Tokyo in Japan. So the aim of this presentation is to present available data on life cycle inventory or life cycle impact assessment of carbon fibers, to discuss how these data have been obtained, as far as we know, and try to find the reasons why these data are so different. And then the expected outcome of this presentation is to come to a better understanding of the differences, the disparity of these data for carbon fibers, and to maybe come to a more harmonized set of data for carbon fibers. So just as a brief introduction, And I always like this slide, which I made some 15 years ago together with my student, who is now CEO of the Reinforced company, Michael Collins. And you see here, this is the bending stiffness, specific bending stiffness, so corrected for density for unidirectional composites compared to steel and aluminium. And we see that steel is the lowest, then comes aluminium, then come glass fibers, and then come natural fibers like flax, and at the end we have carbon fibers. So we see clearly that UD carbon fibers have a specific bending stiffness, which is, as you can see, more than twice the value for aluminium and more than 3 times, almost 4 times than for steel. But there is a but, and this is that as far as we understand, the embedded energy, and that as a metric for the ecological impact of carbon fibers, when you produce the carbon fiber, not when you use it, because then you make the structures lighter and you save energy, but just the embedded energy in the carbon fiber itself seems to be much, much higher than glass fibers and evidently much higher than natural fibers. But the question is, how reliable are these data? So you know how we make carbon fibers. In the meantime, I have shown that in the previous presentation. And if we now make a life cycle inventory and then a life cycle impact analysis of any material or any product, it has 4 steps. We first define the goal and the scope, then we make a life cycle inventory, then a life cycle impact assessment, and then the interpretation. And so if we do this for the material extraction, and we limit it to that, excluding the production of a product and the packaging of a carbon bicycle, for instance, the use and so on, if we limit ourselves to the material itself, then we can first make a life cycle inventory, an inventory of all the materials which are used and their effect on the environment. And then we do an assessment of the impact using different parameters. And then finally, we make an interpretation. We try to understand the correlation and to try to understand the importance of these different parameters. Now, for carbon fibers, it's quite straightforward. First, we do a life cycle inventory. That means we do this for the raw materials, for the energy we need by heat or by electricity or steam and any other input we are using. And then this is what we use as input in the production of carbon fibers. First, we have the acrylonitrile, then the polymerization, the fiber making, oxidation, carbonization, surface treatment. That's what we call the life cycle inventory for 1 kilogram of carbon fiber. And then we go towards composite manufacturing and towards the use phase, which is often much more important than the previous ones. I refer to publication by Professor Takahashi. And then we have the issue of recycling. I will limit myself in the discussion on LCA of carbon fibers. I will limit myself to that first part here in the green box. Now, what are the indicators which we use to assess the environmental impact of a certain material? Well, first of all, we have, of course, the global warming potential measured in kilogram CO2 equivalent. Then the acidification potential measured in sulfur dioxide equivalent, and then the eutrophication potential, which is related to how much nitrogen is coming into the environment, which will impact the balance in nature and plant growth and things like that. A full LCI exercise includes many more different impact categories, radiation, land use, air pollution, and so on. But we will limit ourselves to cumulative energy demand. And the cumulative energy demand is the amount of energy which is embedded in a certain material, and it is accumulated during the extraction of the material, the production of the material, and so on. And we will further use this cumulative energy demand as a kind of proxy also for greenhouse gas emissions, although and for other environmental impacts, although still there is a difference between CED on one hand and GWP, greenhouse gas emissions on the other hand. But we will limit ourselves in this discussion on cumulative energy demand. Now, if you look in the literature, and that's what I was doing together with Junko Takahashi and Véronique Michaud, and we looked back into the 1990s, and if we look at all the data which we have produced up till this year, then we see a very, very large variety, a factor 6 difference in the data just for that simple metric, namely the energy demand for 1 kilogram of carbon fibers. Now, why is that? Well, we started when we started this study with some assumptions or some ideas, some hypotheses, let's say. We thought there are three main ways to get these data. You can do theoretical calculations. Each physical or chemical reaction, you can calculate the ins and outs of energy. Some are needing energy, some are emitting energy, and so on. You can do all these theoretical calculations, or you can do lab scale or pilot scale based measurements, or you can measure data in industry and together with industry in industrial production. So these are already three different ways of getting data for the life cycle inventory of carbon fibers. And hence, our hypothesis was that there is no consensus on how these data are collected, what is the calculation methodology, and what are the measurement procedures. Now, a second one is that there is a difference between lab scale and pilot line data on one hand, and data measured in the industry. And it was our hypothesis that maybe these lab scale and pilot scale data could be overestimations, and I will come back to that, due to a loss of the scale effect and due to the fact that lab scale and pilot scale facilities are sub-optimized processes compared to industrial processes. And then there can be other types of things like system boundaries, type of process, and type of carbon fiber. I can tell you that the data I will deliver later on are all more or less for T300 to T700 fibers, and that the effect of the type of fiber is not that critical. And certainly for CO2 emission, not as much for the energy itself, but for CO2 emission, it can be important whether you produce in Japan, the EU, the US, or China. And that is mainly related to the fact that in all these countries, we can have a different energy mix, fossil, nuclear, renewable, and that has a strong effect on CO2, not so much on the cumulative energy demand. But maybe one of the most important things, and now I'm already anticipating on our conclusions, is the energy flow in the factory. Many companies, just to save money, not to have a lower environmental impact, but just to save money, they use their energy as effectively, efficiently as possible. And hence they are reusing as much as possible waste streams of energy in the same process or in other processes in the company. And that is something you cannot take into account when you only look at pilot plant or lab scale data. And then, of course, there is a different assumptions for the temperatures at which you oxidize and carbonize, the duration of each step, the conversion rate, and so on. So there are many, many reasons why these data could be different. And that was the goal of our mission, of Veronique, June, and myself, to try to understand where these differences are coming from. So as I mentioned, we focus on cumulative energy demand. And out of all the data, we selected, in fact, two data which are important because they are published, two sets of data, because they are published by two organizations which represent in one way or another the carbon fiber manufacturers or the composite manufacturers. JCMA, which is the Japanese Carbon Fiber Manufacturing Association, and UCA, which is the European Composites Industry Association. And they both have data on the environmental impact of carbon fibers. So we will focus on those. So the first time I was confronted with environmental effects of carbon fibers was during a visit of Professor Takahashi at our university, now in the meantime 18 years ago, in 2005. And at that time, Takahashi sensei, he published data which had been, after first initial data, very preliminary data in 99. In 2004, they did a more serious measurement, a more serious study, and the data for the energy demand was about 286, which was later on confirmed in a new measurement in 2009. And you see also the other data for three other parameters. So these four indicators, which I showed, so energy, CO2, SOx, and NOx, they were in Japan based on data collected in the life cycle inventory exercise of JCMA, which they did measurements in three different companies and then grouped these data into the four categories. And this is really a cradle to gate approach where they start from the raw materials, all the energy, all the electricity is included to come up to 1 kilogram of carbon fibers. And then in 2018, which is quite a lot later, almost 15 years after the first data published by JCMA, UCA was doing a similar exercise. And they came up with a cumulative energy demand of 770 megajoules. I remember the 286 of JCMA. Now, this is part of their report, and here you see the CAD data, 771, and the CO2 emission, which was about 39 kilogram CO2 per kilogram of carbon fiber. How did they get these data? Well, first of all, in our discussions with UCA, it became clear that they sought for industry input, but they could not obtain this industry input. The existing carbon fiber companies resisted to give all their data. So they had to rely on data from literature and on data from database like the EcoInvent database. And funny enough, they also refer to one of our presentations, our publications, where we had a very initial study in 2009, but that study was only based on theoretical assumptions and again on the same EcoInvent and other data. So this was again not based on experimental data, neither in lab scale nor in a pilot plant nor in industrial conditions. And they also refer to a very much referenced paper by Das in the United States from 2011. Then 2 years later, they published a new calculation where they then included some experiment-based data, but on lab scale and pilot scale level realized, produced by the University of Aachen in Germany by ETH. And then they came up with an even higher value, 1040 megajoule per kilogram, which then in a later version, they slightly changed again to 998. But let's say about 1000 megajoule per kilogram of carbon fiber. And then during, let's say, inspired by the discussions we had started with JCMA, also the JCMA came up with recalculated data, and I will not go too much in detail. They included then also feedstock energy, but then their number was 350 megajoule and about 20 kilogram CO2 per kilogram of carbon fiber. UCIA was quoting, if I remember correctly, was quoting 49 kilogram of CO2, so more than double. So what is the situation we have? We have the situation that UCIA is quoting a value, this one here of 1041, which is slightly decreased to 998, and JCMA has this value of 350 megajoule per kilogram. And remains the question, why is there so much a difference? And I just wanted to make a kind of comparison. If somebody would sell you 1 kilogram of carbon fibers or carbon fibers, and they say the value of the stiffness is between 200 and 600 gigapascal, you would not trust that person, because giving such a big range of mechanical properties is simply unacceptable when you design a composite product. Well, we have exactly that situation when we are talking about environmental impact. We know that the value must be somewhere in between those two, in between 350 and 1040, but that is still a factor 3 difference between those two data. So at first sight, we thought a similar approach is used, and after some discussions, feedstock energy is now included in both. And I maybe have to tell you now first that since about 1 year, or almost 1 year after my visit to Japan in September, we now realized some direct discussions, online discussions between people from UCIA and people from JCMA, which is a real breakthrough. At least they both collaborate now with us, with Jun Takahashi and Veronique Michaud, to clarify this problem. So UCIA, as I said, about 1000 megajoule per kilogram. Their measurements are based on laboratory and pilot lines, on theoretical estimations, and on databases and literature data, because they could not obtain data directly from carbon fiber manufacturers, whereas JCMA uses data measured in 3 major carbon fiber manufacturing companies, Toray, Mitsubishi Rayon, and Teijin. And they do these measurements following ISO standards. The data are then collected by independent experts and reviewed by them. And these data were based on a total production of almost 7,000 tons of carbon fibers in 2017-2018. And the aggregation to us is confidential because the companies do not want to have their own data published as such, only as an average value for the 3 companies. But anyway, the way these data are measured and aggregated is according to ISO standards. So now that we know how these data are produced, what can be the reasons why they are so different? And we have a few hypotheses. First, the conversion ratio. UCIA is assuming that you need about 2.4 kilogram of polyacrylonitrile for 1 kilogram of carbon fibers, whereas JCMA measures in their plants a conversion ratio of 2.1. Of course, it's in their interest that that conversion ratio is as low as possible, because the lower it is, the lower the amount of polyacrylonitrile fibers you need for producing 1 kilogram of carbon fibers. Second, the energy used for the PAN production itself is not clear. They quote LCA 136 megajoule per kilogram. When you multiply that by 2.4, you end up with something which is around 400 megajoule already only for the polyacrylonitrile. And then you still have to do the oxidation and the carbonization. Whereas we know, and if you look in data bases, we know that for polymers, the amount of energy needed for producing 1 kilogram of such a precursor of such a polymer is between 50 and 60 and 70 megajoule. So this is something which is not clear at all. And where we are working in getting more detailed information. A third reason why this is unclear is that LCA quotes that 820 megajoule of the energy needed for producing carbon fibers, both in the acrylonitrile, the PAN, and the oxidation and carbonization phase, altogether, the electricity accounts for 820 megajoule and heat only for 170 megajoule. Whereas in the JCMA data, the electricity is only about 93 megajoule and 65 megajoule internal, 27 megajoule external, and the rest of the energy comes from fuel, natural gas, and which is of course much more efficient, because if you first use fuel and gas to make electricity, and then you use electricity again to make heat, it's not a very efficient process. So we have more data on that, but I just want to mention that the JCMA data use less than 30% of pure electricity energy, whereas the LCA data have more than 80%. Why this is like that and what is the consequence of that still needs to be clarified. And finally, there is a big impact of economy of scale, depending on the amount of carbon fibers you produce. And this is a recent publication by some Japanese researchers. If you go from 500 ton per year to 3,000 ton per year in a certain production plant, then you see that the CO2 emission is going down from 43 to about 24 kilograms CO2 per kilogram carbon fiber, and you end up with a value which is very close to the value in this JCMA data. And the reason for that, of this economy of scale, is of course the potential for heat recuperation in large scale production and the level of process maturity. The more you produce, the better you understand the production, the more efficient you can make the production. So this is a fourth reason why there could be this big difference between the high LCA data and the low JCMA data. And then there is an unexpected independent voice which came up just a couple of weeks ago during the ICCM conference in Belfast, where Badr Mutik, who is a researcher at the Plymouth University, made a kind of evaluation, a meta study, an evaluation of the quality of the life cycle inventory data for composites or for components of composites. He was doing it for glass fibers, for carbon fibers, but also for polyester resins and for epoxy resins. The way he did it, you can read it in this publication. But what was interesting, so he looked at the reliability of the data which were generated, whether they were coming from industrial measurements or from just databases or from literature or from theoretical, and the way they have been following the strict ISO standards and so on. So all this was evaluated, and then he gave a kind of a global score. And what is interesting is that for carbon fibers, the LCA data, there were only others, the EcoInvent data, the Sphera, I will not comment on that, but the LCA data were considered to be not reliable at all in that independent study, whereas the JCMA data were considered to be the most reliable. And what is even more interesting is that the LCA data published on glass fibers were considered to be very reliable. And the reason they quote in their paper is that because these data are based on glass fiber data measured in industrial plants. LCA being initially a glass fiber Glass Fiber Composites Association had direct access to data based on measurements in industrial glass fiber plants. So what we learn from this is that according to this independent quality assessment of LCA data, that the data which have seemed to have the most trustful, the most reliability, the highest reliability seem to be data which of course follow the ISO standards, but who also are based on industrial input, the carbon fiber data from JCMA and the glass fiber data from LCA. So our preliminary conclusion is that the industrial versus the lab scale data and the theoretical assumptions, this is maybe the main reason for the big differences in input data. And this is confirmed by this independent comparison by the people from University of Plymouth. And then a second unknown, which is further needs clarification. And a third one is the large difference in electricity consumption on one hand, and the difficulty to compare data sets for the PAN production itself. So these are our preliminary conclusions. So there is no simply true data, but after our study, we assume or we believe that JCMA data seem to be adapted for analyzing composite processes, the environmental impact of composite processes when you are using carbon fibers. What we further are doing now is critically analyzing all the published data, creating harmonized CAD or LCI data sets based on industrial reality, performing sensitivity studies we would like to do, and further broaden the discussion from CAD to all the impact categories, to greenhouse warming and so on, land use and so on. And we are continuing our meetings with the interested parties for better comparing the data sets and better understanding these differences. So thank you very much for your attention, and with the best regards from Professor Takahashi to the left and Veronique Michaud in the middle, we three together at the ICCM in Belfast a month ago. Thank you very much.
Thanks a lot for the great lecture. So feel free, Ignace, if you want to take a break.
No problem.
So for the questions, if you can also, people, just raise your hand, so I can make you co-host if there's a question. So meanwhile, until some questions are coming, in your opinion, what's the most tricky thing or the bottleneck for doing LCA? From your presentation, what I understood is just basically gathering data from companies, from different processes, how much energy is required to produce chemical and then product itself. It seems like a huge effort. Like, is it really realistic to do such?
Yeah, I think that's the main issue, and it's in a way understandable that these companies are not so let's say open to give all the detailed information on their processes, because then they will also give away some of their production secrets. If all of a sudden it would appear that in one or the other process they are using 10 times less energy than their competitor, then the competitor will look very closely into that process and to see whether they can learn something from it. So in that sense, the approach of the Japanese Carbon Fiber Manufacturer Association was, in my opinion, very clever. What they did is they made measurements in 3 companies according very strict to the ISO standards and supervised by independent experts. And then these data were brought together to a third party, an consulting company who is experienced in life cycle analysis, and they kind of aggregate those data from the 3 different companies. The 3 companies do not even know each other's data, so they are just aggregated, and these aggregated data are then published and are published in as much detail as possible. We as external, let's say, evaluators, June, Veronique and I, we still would like to have even more details on these aggregated data. They have a report of about 25 pages, which is available on the website of JCMA. And you can have a look in there, but it's our feeling that we even would like to have a little bit more detail. But I think that is the furthest we can go at this moment.
Thanks a lot. So Robert Prof from Lille University. So Ken.
Hello, thank you very much for very nice lectures. Really,
Hello,
very
Robert.
informative. Hi. I have a question because I'm not so experienced in LCA to say the least. But if I now sit down in front of computer and start using some software which does LCA, if I don't do this very comprehensive analysis of fiber itself, but start from the data which they already have for a carbon fiber and do it for composite structure, where do I end up? I mean, what do they use for carbon fiber? How do they come with this? Because they have databases, but it's like a black box, I suppose.
Yeah. Well, that's what we suggest in our discussion, in our conclusion, that let's say you can use the data which are, for instance, in EcoInvent. EcoInvent is one of the basic databases which people who are doing LCA studies are using. There are some other databases around, but they all, or up to as far as we see it now, none of them is using the data as published by JCMA. And that's in a way very surprising, because they are using data for glass fibers, which are coming from the glass fiber industry, but they, in one way or another, refuse to use the data from the carbon fiber industry, which, according to us and to this independent study by the University of Plymouth, clearly is more reliable than the data from LCA, which is based on the EcoInvent data and on some further lab scale and pilot scale measurements. So my suggestion or my hope is that as quickly as possible, we can convince, for instance, EcoInvent, and Veronique Michaud is working on that because she is member of the board of EcoInvent. We are working on that to get the data from JCMA into the existing databases. But I would suggest everybody who is using the existing data to tell, okay, I have been using these data from EcoInvent or from LCA or whoever, but be aware that there are other data which are 1/3 of the value of the data of EcoInvent and LCA. And we have, for instance, been doing already 15 years ago measurements or calculations on if you replace steel or aluminium by carbon fiber composites, how much on the long term, because you make the structure lighter, how much on the long term you save on environmental impact during the whole lifetime of, for instance, a car. And of course, the value you start with for 1 kilogram of carbon fiber to compare to 1 kilogram of steel or aluminium, the starting value, if you take, for instance, for energy, and instead of 350, 1050, then of course you have a totally different picture. So it's very important that we use as precise as possible data. And our suggestion is now clearly look at the JCMA data. If you don't have them available in your database, then use other data, but give a clear remark that there are other data available on the market.
Thank you very much. That's very important because, as you said, otherwise you can get whatever results you are after.
Exactly. For instance, the changeover point after how many kilometers a carbon fiber car is less energy demanding than the break point, the break-even point. That can shift from, let's say, 100,000 kilometer to 50,000 kilometer,
That's really...
simply depending on the start value you use.
Well, thank you very much again. It was really interesting. Thank you.
Thank you, Robert.
Just checking if there are more questions, but it seems that much. Oh, okay, something came. So Patrick, I will just wait. I will make you co-host. There you go. You should be able now to open your mic.
Okay. Thank you again. Similar to also like Robert, thank you for an interesting presentation. A bit of a follow-up on that. How to a majority's discussion here is on some virgin carbon fibers and how to treat virgin carbon fibers in a life cycle analysis. How about recycling of carbon fibers and how to account for that in do you have any views on how to where to handle recycled carbon fibers, sort of where to put the life cost? Is it on the first product, distribute it on several, or?
Yeah, that's of course a very important discussion, the allocation problem. I'm not a real expert in LCA, I have to make clear, but I know that in LCA, this is a problem all over the LCA world, where you allocate your environmental impact. Certainly, if you start talking about recycled materials, do you have then your allocation of the initial product, of the initial environmental impact to the first product you make? And then you stop and you start again from zero. And then you say, what I further need for recycling this material is then my environmental impact of the recycled material? Or do you have to take into account already the previous environmental impact? So that is the allocation problem. As far as I know, there have been studies, amongst others by Professor Takahashi from University of Tokyo, and he has several. I could share it with you, but I'm afraid I will not find it immediately. He has some data where he drastically shows how much the environmental impact of a carbon fiber, if you allocate to that recycled carbon fiber only the energy or the CO2 emission you need for making the carbon fiber, that environmental impact is, I think, almost an order of magnitude lower than for a virgin carbon fiber. And so in that sense, there are a lot of reasons to use recycled carbon fibers. The question is now, do we agree on this allocation model? Do we agree to allocate all the energy to the virgin product and then start from more or less zero, because you have to collect the material and so on, and then calculate the environmental impact only for the recycling process as such? That's a fundamental discussion, and I'm not enough LCA specialist to know what is now in the LCA community accepted as a correct way of doing it.
Okay, thank you.
There is one more question. If you have time, we can. So, Zainab Al-Makdasi. So, the question is that is there an effect of when the data has been added to a certain database and how that is changing over time? Is it a matter of few years or few decades?
Oh, that's extremely hard to answer that question, because as far as I know, I'm not a daily user of LCA databases, not at all. So I have to rely on what, for instance, Veronique Michaud tells us in our discussions, and her statement is that for instance, the EcoInvent databases are based on let's say what they can find as publications on, but you have to be very careful, because in a lot of publications on LCA of carbon fibers, for instance, people refer to always the same previous publications. And it's very difficult to find original publications which have done the whole calculation by themselves. And for instance, it's not surprising that our initial data from 2009 and the original publication from ONRL from DAS in the US from 2010, these seem to be the most cited publications on LCA of carbon fibers, because these two have done an attempt to make the full calculations by themselves. And a lot of more recent publications are using partially these data, adding a few other measurements or calculations. So it's you have to be very careful. So in that sense, I think I hope that as quickly as possible we can come to an agreement between JCMA and EUCIA, that they come up with a kind of joint methodology and joint data set, which then will be distributed to the different existing databases worldwide. By the way, final remark, the European Commission is also working on their PEF, product environmental footprint methodology, which is in fact a kind of enlarged LCA analysis for products. And that is a very strict methodology, which is partially based on ISO standards. And that will have to be followed for all products which are produced and consumed in Europe. So there will come a very strong push from the European Commission to have reliable databases. And in that sense, we should hurry up. We should really act as quickly as possible and come up with a reliable database for carbon fibers.
All right. A lot, and I think don't have much question, and so it's now 1 hour 33 minutes since you have started your presentation and answering the question. So thanks a lot. You already took quite a lot of overtime to answer the question and also describe the details. We really appreciate, and it was really an honor to be with you this session. Royson, do you have anything else to mention?
Just thanks a lot. Thank you very much, Professor, for accepting our invite.
Yes, you're honored.
It's inaugural talk. We are extremely honored, Sampa Finland, on behalf of entire Sampa Finland board. We would like to thank you very much for this wonderful presentation and wonderful discussion. And let's have a very good collaboration in future.
Thank you very much, and thank you for giving me the opportunity to talk to so many people, not only in Finland, but also in Japan and other countries. And I'm very open to further discussions on this topic, on those two topics with all of you. But thank you for giving me the opportunity.
Thanks.